I'm very pleased to introduce our next speaker, my good friend Anirban Bandyopadhyay from NIMS in Tsukuba, Japan, who will be speaking on photon vortices emitted by a neuron, protein, and a microtubule. Anirban.
Okay, thank you. And very good afternoon to all of you. So today I'm going to talk about optical effect on microtubules, neurons and proteins. Primarily, we would like to test quantum properties of these materials, and I would try to be as simple as possible. If you don't know what is microtubule, then microtubule is a nanowire, 25 nanometer diameter, and a few hundreds of micrometers long. So you can see transmission electron microscope image, TEM, so high energy beam passes through, and if we pump the temperature, it tries to survive. And top right corner, you see there are 3 layers. In the inner core, there is a water channel that is ordered water, crystalline water, and then you have tubulin protein layers, and then you have C-termini others. So we have done the measurement of microtubule, electromagnetic resonance measurement, and those water channels vibrate very fast in the gigahertz frequency range. Proteins vibrate in the megahertz frequency range, and C-termini in the kilohertz frequency range. To the bottom right corner, you can see quantum tunneling images with a scanning tunneling microscope, where you see how one side of the microtubule to the other side, how a charge can pass through. So these are very old results, and this is just to introduce you to microtubule. And from the microtubule, you can take out one tubulin protein, just 2 nanometer. And with quantum tunneling images, you can see it. What you are seeing here to the right is the actual structure of the tubulin protein, and you can see to the left side, it's changing. The protein looks very different when you resonate it with different frequencies. It is almost like you compose a music and it dances to its tune very differently, but its shape, its size, and how it looks like, it changes. So this is also a very old result. You have seen tuning fork. So tuning fork, if you hit it, it vibrates resonantly with a particular frequency. But if you try to look at microtubule or any biological material, surprisingly, you will find that they vibrate with many different kind of frequencies. Many different kind of frequencies, as if somebody has taken large number of tuning forks and have put them together. But those frequencies are not random. They club in a group, and then the group behaves in a unique fashion. They have a particular phase signature. So there are many people, some of the people are present here, many people have contributed to the understanding of microtubule, and you will find in literatures reports of super radiance from microtubule birefringence in 1990s, 1995, 2005. But what we did is vortex entanglement, quantum interference, quantum teleportation, and quantum tomography. Quantum tomography and quantum teleportation is currently ongoing in our lab. And today I will introduce you how in a laboratory you can design experiment, quantum experiment, and what are the key things you should remember if you really want to do quantum measurement. So what is a quantum effect? You have seen this kind of energy level diagram in the textbook, where you will see that in the excited state, there are many, many energy levels, but the bandwidth of the level should be less than kBT. Kb is the Boltzmann constant, T is the temperature. It is the available energy in the environment. So in the environment, suppose it is a room temperature, then it is 0.023 electron volt. But if that gap is more than that, then the measurement will be done. Entanglement is not possible. That's why many people argue that look at room temperature, you can never realize quantum effect, because very difficult. How do you do that? So that's why many people, they reduce the temperature to the freezing temperature and try to reduce the kBT, that is Boltzmann constant, to the temperature, the product of that term. However, there is a way to do it. And how did we do that? Here is a graphics. Suppose you have a helical nanowire and a photon is passing through in a helical pathway. When it will project, it will be a ring. It is called a vortex. Vortex can have, it is almost like a spin. But if you put it on the, project it on the wall, you will see a light ring. It has an angular momentum. So light photon rotates. It doesn't go straight path. So in 2018, you saw that for this particular discovery, they got the Nobel Prize because light, it can rotate the light. Now, there was another beautiful work. It was done also in the 2000, that when you have double helix, helix means one helical symmetry pathway, and then another twist, then what you can get is light ring with some dark spots and light spots and bright spots. So it's a ring, somewhere it is dark and light. So if you have that, then there are two angular momentum in it. Now what we did, interesting, is the third one, when you have three different kind of helical symmetries which are there in the microtubule, then what you can do, you can send the light, you can apply three angular momentum, one perpendicular to each other, and you can get a sphere, a 3D geometry of light. So one vortex is one spin. You can understand, as I have explained to you, that a single electron spin or single spin or magnetic spin, whatever be that state, it cannot survive in microtubule. It is impossible. But if it is an optical vortex, then it can survive in room temperature, the quantum state. It is there, there are several evidences. But still, if it interacts with a matter, then measurement is done. Then what would you do? Then, if there are multiple different vortices, they come together and create a 3D geometric shape, then it is very difficult to destroy that. And it can survive in room temperature and interaction with matter. I repeat it. If you have multiple vortices, and you suppose you have a cube and 8 rings on different 8 surfaces, then you can survive it. It can survive. So there is a possibility of survival in the room temperature, an ambient atmospheric condition. So you have seen different research papers like protein complex in plants, and for photosynthesis, protein complex shows quantum phenomenon and this kind of reports where ultra-fast laser pulses, femtosecond pulses are sent and they show quantum effect. I'm sorry to say that never proves that there is a quantum effect in the proteins or anywhere, because laser source is a classical source. The photons are not entangled. So you have to convert your photon source into a quantum source or single photon source to do any quantum experiment you want to perform. And how to do that? Normally you can purchase from the market single photon source, which is very expensive, but there are many researchers who are coming out trying to come up with a very different kind of sources, very different ways of doing it. One very cheap way that a very low cost way we found is we take the picosecond pulse laser, then we take a pair of magnet, then ferromagnetic fluid, and we have a very special kind of thin film, magnetic film, where we have nanowires which rotates in the presence of laser light. So from laser light, pulse laser, we convert into a single photon. Single photon does not mean one photon. Single photon means you have 10 to the power 14, 10 to the power 15 photons, but all the photons are entangled into a single state. If you can create this, only then you can do the quantum measurement. So we did it, and this is the experimental setup where you have a coincidence counter and then you divide it into 2 parts, and we normally use it to measure molecular motors and others. But there is another very interesting aspect. If you want to do really quantum measurement, you need to do another thing. That is, suppose microtubule or any biomaterial, it has many different components in it, right? And even a single molecule, it has many different functional groups and different orbital interactions. So if you really want to understand the quantum properties, then not just a single photon source, you need to do something more. And that is, by fine-tuning the single photon, you have to create the entangled collapse in multiple different time gap. Only then, to the right side, extreme right, you can see that the single photon source that we create, we divide it into, split into equal time gap. And then we bombard it on a single molecule, a molecular structure, or whatever the biological structure. We want to prove that it is a quantum system. So what I said is three things. Normal laser light, normal light, it's impossible. Normal laser light, impossible. You need to get into single photon, and what you have to do is you have to split it into different time gap or time collapse, so that you can really probe different kind of entanglement, different time domain entanglement that is there in the single molecule system. And if you want to study more, you can check why quantum computers are necessary. They say that in nature, the reality is single molecule has quantum properties. If in future we realize quantum computer, then we will be able to understand nature for the first time in the true sense. Why do they say so? Because in quantum computer, you'll be able to control the different layers of entanglement. So this is to the right side, you can find that how did we do it. So how the difference happens, in the top layer, you see pulsed laser. Laser means same amplitude, same phase, same intensity, and still you will find that in different time domain, that kind of gap is there. But when you go to the single photon, then you find we have created topological photon. You can see a dodecahedron is there. So this kind of dodecahedron or other structures are produced from microtubule. So we have patented this technology to create the quantum computer using microtubule-like devices, elementary devices. Then there are many semi-classical responses. For an example, you take a microtubule, you allow it to do the conductance measurement using capacitance fluctuations, and you can find periodic oscillations. So periodic oscillations, whenever you get, there is a possibility that the whole system is vibrating as a quantum resonator. There are other things you need to check. I think before me, one of the speakers presented that there are magnetic field in the brain, and magnetic field is very important. If you want to check magnetic film, then you need a magnetic sensor. And then sensors, so in our laboratory, in the last 17, 18 years, we have developed a series of sensors where we call it differential sensors. That means you will have two different electrodes with two different properties, and you take a difference between the two, and then you take the signal out. So you can see here a terahertz sensor and a magnetic sensors to the top right, that is helium ion microscopic image. So you can create this kind of nanoscale systems very close nearby, and you can touch. So it is just like a pin. On the top of the pin, there is almost single atomic structure. Okay, so that kind of structure you need to build, and you can see with tubulin and microtubule, we could find out the magnetic interference. The second thing I would like to talk about is that I understood in 2012, 2013 that we have to develop a technology to image neuron or other systems without making a physical contact. How can we do that? Suppose you can see that there is a neuron image, and what we do is we send electromagnetic frequency signals and try to image. Just like I am looking at you, photon is there in the visible range, and I am getting the reflection. It is coming to my eye, and with the sensors, I'm seeing it. But what if I look at only X-ray? Then all these people to me will appear like skeletons are sitting over here, right? Similarly, I can change the frequency from the laser frequency to, say, microwave. Then how does it look like? So that kind of image is over there. So we can change the resonance frequency of electromagnetic resonance frequency, and without touching the neuron, we can find out. So in the middle, you see some 200 nanometer gap. There is a beautiful ring that is actin and beta spectrin crystalline structure just beneath the neuron membrane. And below that, there are microtubular bundle. So without touching it, you can find out what is going on. And then this is the kind of sensor we use, gigahertz sensor, to take out the different frequencies. Always remember that if you want to have a high frequency sensor, it should be very close to the probe. If it is far, if you take a cable and then if you have a large amplifier far distance, because there are many commercial systems where I see that they give you a big cable and a probe, and you have a long distance, far separated the instrument, you can never get the reading. You have to amplify it very close where the probe is. And then you have a patch clamp. So patch clamp and the electromagnetic channel side by side. But if you do that, what do you reveal? So 1907, Lapik proposed that neuron's membrane is communicating. So that remained there in the textbook until now. But in 2016, we started, from 2016 continuously we have been publishing. All our papers, you can get it in ResearchGate. You don't have to pay $40. But, so you can see that a membrane is communicating, and then when you go inside the neuron, you see microtubule bundle and beta spectrin and actin crystalline structures. So what we found by sending single photon to bombarding it on the neuron and simultaneously resonating it electromagnetically. So please remember two things. If you do any quantum measurement, two things are necessary. One, single photon, which you will send it and see the effect on the photon. And second, most importantly, you have to resonate the whole structure using electromagnetic wave. So two signals must be simultaneously pumped on the material. Because without resonance in the room temperature system, you can't do quantum entanglement or other kind of measurements. So there are pair of rings that are generated. So that's why we say that we need revolution in neuroscience, because there are structures that is inside the neuron membrane. And why it is important? Because all of us say our conscious thoughts. How do we get the conscious thoughts? So in our neuron, the spikes are there, and we fine-tune the time gap between the spikes in milliseconds domain. But neurons vibrate in the milliseconds domain. How can we believe that we control we have a millisecond resonator, that is the membrane, and that can control millisecond firing? There should be something which is inside, which can control the millisecond firing. So microtubules vibrate and resonate in the microsecond time domain. So there are several papers where we have measured simultaneously the patch clamp and the microtubule resonance with coaxial probe simultaneously. And we have shown that 200 microseconds before a neuron pulse, there is a signal transmission through the microtubule. And there are a series of papers. And this is one of the videos where we have taken with electromagnetic resonance. To the left, you see a neural network, 3 neurons. And if you measure at the millisecond time domain how the ion channels are resonating, and to the extreme right, we look at the same neural network in the microsecond time domain. And you will find that electromagnetic communications in the megahertz frequency range is happening much before. In the middle image, you see that there is no sign of firing. Only soma and other soma to the two different parts. Now the firing is happening. So you see ion channel is transmitting, but already the firing of microtubule and other filaments have finished. So you can do scanning dielectric microscopic image or resonance image of the neural network to say that the fine-tuning of timing is done there. I understand in 1952, Hodgkin-Huxley did the experiment. He melted the microtubule, and he said that still the neuron fires. But what he didn't do, or what people didn't do, was that, can you modulate the time? Because if you cannot modulate the time, you cannot have cognitive effect. You cannot explain the cognitive effect in the brain. So this is the kind of setup. So we have a single photon source, we have a microwave antenna, and we try to detect this ring in a different way. And we also check different vortex formation. We project it on the wall to see how the vortices are getting generated. And these are the results. So you, with this antenna, we can fine-tune what is the product that we want to see. And we can look at the vortices produced. I know the result is noisy, but believe me, if you do the real-time experiment, you never get clear-cut pictures like the photonic researchers show you. With the biomaterials, very difficult. So often when we send this paper, for the reviewer says, your pictures are so dirty. What do you say? I mean, we are not doing the pure photonic experiment. It's a biomaterial. It has so many different materials, and the dynamics are there. So so be careful when it goes to the photonic experts. But you can see that it's a combination of rings. So we can change the resonance frequency, and we can send a single photon, and we can see many different kind of combinations of light or vortex that is generated. We have made a rigorous effect. So you can read this paper, and that is in detail, and we have tried to map a neuron, a microtubule, a protein, in terms of this kind of vortex structures. And we have found the periodic oscillations in the resonance band, and we created the 3D architecture of clocks, and we solved the Hamiltonian. I would like to draw your attention to the bottommost part. You see, when we bombard the photon to the microtubules or microtubule bundle, we see that there is a holographic system. But if you change the frequencies, you will find there are 12 holes on a sphere. The 12 holes or singularity regions. But if you fine-tune the frequencies, you can reduce the number of holes from 12 to 0. At certain time, you can find you get just a sphere. So you can control the information content in the microtubular structure. So we patented this, and we created several organic replica of this kind of device where we think that at least 12 qubits we can control using a single system. How it will be useful for computing, we don't know, but we can. So we have created length, pitch, diameter, and this is the experimental setup, integrated setup, and by changing length, pitch, L for length, P for pitch, and D for diameter of the nanowires, and we could control the vortices that is coming out. And of course, the magnetic vortex over there. Let me show you. So it used to take a lot of time, and whenever somebody used to visit in our laboratory, we could not. So now we are taking with a magnetic film the live imaging of different vortices blinking with each other, and we are deconstructing the image to find out how we could. This is simple. You can see the beaker is there, camera is there, magnetic film is there, and then we are trying to find out where the angular momentum of the photons, if we can find out in the light. So we did interference measurement, and we found some fractal patterns in the microtubule by changing the frequencies. One interesting result I would like to say, that if you are checking, if you want to check quantum properties, the most important result is Bell's inequality. What is Bell's inequality? Suppose two objects are entangled. For an example, one person over there and one person, Thomas, over here. And they should have some property, say phase is entangled, or some property is entangled between the two. Now, shared existence means, suppose I measure that gentleman who is in the left, I will get not 1 maximum allowed value, but 1.4. But to the right, if I measure him, I will get maximum allowed value 1, I will get 1.4. So together, I will get 2.8 instead of 2. So it's classically maximum allowed value is 2, but in quantum, measurement, we will get much more than that. So when we get much more than the classical limit, that time we can say that there is a quantum phenomenon happening. And if we fail to do Bell's inequality test, then there is no quantum at all. So as simple as this. I mean, this is kind of a primary test. After that, other explanations could come. But if we are not getting it, that means we are not ready. The system is not ready. So what we did, in this case, this is an old experiment, old paper, because we could not, that time, we could not create, we used to do, it's called BBO crystal, so where the wavelength is doubled. This is a standard way in any quantum laboratory they make single photon source. But the problem with this kind of photon source is that intensity is less, you cannot use it for computing, and many problems are there. After one interactions, it's useless. But later we understood the problem, and then I talked to many quantum computing experts and then asked them that what to do. They say you have to create single photon source in your lab. So this is an old system, and when we have two solutions and microtubules, and we electromagnetic antenna, we excite them, and the B below, you find that the total angular momentum has to be conserved for different frequencies when we tune it. And this kind of results, where sum of the angular momentum for both the beakers is plotted, which is kind of conservation. Okay, I understand it. So this is the last slide I would like to finish. One of the brilliant features that so far we discovered for microtubule is vanishing of the microtubule from the surface. So when we do quantum tunneling, so as you can understand now, our lab's expertise is that we apply microwave and do quantum tunneling measurement. Apply microwave, apply single photon. So two different kind of measurement we carry out. So if you visit my lab, then you will find many instruments, but single principle, single photon and something, resonance. So resonance feature is common. So quantum tunneling is going on, and you will find that by changing the frequency, I can measure the water channel up top. With megahertz, I can measure the tubulin, and in gigahertz, this is the water channel inside. And at certain frequencies, I can also vanish, disappear. The microtubule from the surface, you see the flat surface, and then you can come out. So it is called quantum cloaking. It's a very interesting and known phenomenon. And finally, I would like to thank you for having patience and trying to understand.
Anirban, we have time for a couple of questions from the audience. Gentleman right here.
Second, step by.
Thank you. I'm a neurologist from the University of Toronto. First time here with this group, so I'm new. I'm here to learn. Having said that, what I'm hearing, at least from some of the talks, is that the brain may or may not be relevant to consciousness. I heard some of that. I hope I didn't.
Well,
but let me just finish. I mean, no matter how you look at it, and I'm talking as a neurologist, no matter how you look at it, whether consciousness is quantum or not quantum, the brain has to be part of the equation. The microtubules, I mean, they're in other parts of the body too, but they're in the brain. So regardless of how you look at this, you gotta factor in the brain. To say that consciousness, you can say it doesn't just involve the brain, but it has to interact with the brain. And I thought I was hearing some things to the contrary. Even with language, okay, and I'm a behavioral neurologist, people saying that language isn't in the brain. You get damage to a part of the brain that deals with language. The language isn't normal, even though they can speak. So I just want to put a plug in for the brain.
Thank you. I don't think anybody's arguing with that. The point I think we're making, if you heard Pavlo's talk, Most views are looking at the brain as a bunch of neurons, membrane only, operating from 0 to 40 hertz. Anirban's showing us if you go into the microtubules, you get kilohertz, megahertz, gigahertz, terahertz, all the structure, all this information. So I think the people that we heard about in the first talk, the mainstream theories, are cheating the brain and only looking at cartoon neuron versions of the brain or cartoon versions of the brain per se, and Anirban and others, including myself, are looking deeper at more at the actual biology that's really there. And it does include quantum, whether other people like it or not. It's just a fact. Thank you.
Just, I would like to say that I very much appreciate your comment, and I totally agree that brain should not be the essential thing for consciousness. If we are able to understand one day, when we are saying, I have not presented it today, because today the session was very different topic. The session was about optical measurements on neuron. But I feel that Stuart said, no, the resonance frequency chain, triplet of triplet, are different kind of symmetries in the frequencies. So these mathematical structures that we are getting scale-free manner in different layers, not in the biological system, in many, many different systems. So we believe that maybe the whole universe follows a very mathematical structures. And wherever you realize it, how you realize it, it could be different. Maybe in far distant galaxy, it is not the brain, or somewhere, some complete different system has developed that kind of mathematics or mathematical structure and could realize consciousness. So I very much, I'm very much into that faith that this kind of mathematical formulations is responsible for consciousness. And when we discover it, that will be the most beautiful thing. We would be able to understand that is surpassing whole universe, maybe. But today was not the topic, actually.
Anirban invited everybody to visit his lab in Japan, but he actually has a lab around the corner where he's demonstrating what he'll talk about Sunday of detecting megahertz and gigahertz from the scalp. And I think we better cut it there and
Unless there's
come
a
back
fast-burning one, but otherwise,
at 3:45.
No. Yeah.
One quick
back.
question, but be brief there.
Very
Mark.
brief.
I'll be really brief.
Hang on.
I'm going to make a plug-in for disease and pathology in experimental research, particularly hearing from Christoph about the work with sheaths. Somehow, this is just a suggestion coming more from both theory and clinical side. If we look at multiple sclerosis, damage, fundamental damage, and in very localized locations that can be physically mapped with MRI, for instance. And then in Alzheimer's, specifically microtubule damage within the axons. So I'll be short. There it is.
Okay. Thank you very much. Everybody will be back here at 3:45.